Okay, now in this session we will discuss about the equivalent circuit diagram of a three-phase induction motor. It is somewhat similar to that of a single-phase transformer, but before moving to the equivalent circuit diagram, let's understand the concept of slip in the case of a three-phase induction motor. So we have learned that in the case of a three-phase induction motor, when we give a three-phase AC supply to the stator winding, a rotating magnetic field will be produced, and the speed of that rotating magnetic field is called synchronous speed, which is given by ns is equal to 120 f by p, right? And when the stationary rotor conductors are placed in this magnetic field, an EMF will be induced, a current will flow, a torque will be generated due to interaction between the current carrying rotor conductors and the rotating magnetic field, and this torque will cause the rotor to rotate. This already we have learned. And let nr be the speed of the rotor. Now we have seen that the rotor always try to catch up with the synchronous speed, but it can never attain the synchronous speed. That is, the speed of the rotor will always be less than the synchronous speed, and that difference you call it as slip speed, or you can express it as slip. So slip, the equation for the slip is given by small, it is usually represented by the letter small s. It is given by the difference of the synchronous speed ns and the actual speed of the motor or the rotor. So this is called the slip speed, and this by ns. This is called the slip. So slip is given by the ratio of relative speed to synchronous speed. Usually it is expressed as percentage of fraction, so you can write it as into 100. Okay, so this is expression for the slip. So what is slip? Slip is a ratio of the relative speed to the synchronous speed. What is relative speed? The difference between the synchronous speed and the rotor speed. Now we can cross multiply this. From this we can take it as equation number 1. So when you take, or when you find the relative speed ns minus nr, we can write it as ns minus nr is equal to what? When you cross multiply from equation 1, it will be equal to s into ns, right? Now we can bring all the ns terms to the left hand side. So what will s will come to this side? So 1 minus s into ns, that is the synchronous speed, will be equal to nr. So how can you find the actual speed of the motor? That is rotor speed, 1 minus s into ns, where s is the slip and ns is the synchronous speed. Usually we express slip as a percentage, so it is ns minus nr by ns into 100. So this is actually the expression for the slip. Now what about the value of the slip? At normal load condition, it will be ranging between 2 and 5%. Okay, 2 by 100 or 5 by 100, between 2 by 100 and 5 by 100. At no load conditions, its value is very small, it will come up to 0.5%. Okay, so this is about the slip. Now we will see the frequency of the EMF induced in the rotor. So we know that the synchronous speed, what is the expression for the synchronous speed? The synchronous speed ns is given by 120 f by p, where p is the number of poles and fp is the supply frequency. Okay, so initially when the rotor is stationary, there is a rotating magnetic field. Initially the rotor is stationary, right? So that time the stationary rotor conductors are being cut by the flux, okay, which is running at synchronous speed ns. That is, when the rotor is stationary, the conductors are cut by the flux, which is rotating at synchronous speed. But what when the rotor starts rotating? Initially we are considering the condition when the rotor is stationary, but now the rotor starts moving. So the speed is not the synchronous speed. We have to consider the relative speed, that is ns minus nr. Okay, so that's a point here. That is, when the rotor starts revolving, the rate at which the rotor conductors are being cut by the flux, it depends not on the synchronous speed but on the relative speed. What is the relative speed? Ns minus nr. And we can write the expression for this relative speed, that is ns minus nr, as 120 f dash by p. It is not f, it is f dash. So we will find the expression. What is this f dash? That is, what is the frequency of the EMF induced in the rotor? That we will find out. That is represented by the letter f dash. Okay, so let me take this equation as equation number 2. So from this equation number 2, what will be the value of f dash? Just cross multiply. So it will be ns minus nr into p by 120, right? ns minus nr into p by 120. That p by 120 I can write it as 120 by p. Okay, so f dash is equal to ns minus nr by 120 by P. Now we will further simplify this. Now already we have learned the expression for the slip, which is given by S is equal to relative speed by synchronous speed. Now when we cross multiply, what we got? Ns minus Nr is equal to S into Ns, right? Okay, and what is Ns? Ns is equal to 120 F by P. See here. So I got the expression of Ns minus Nr as equal to S into 120 F by P. Okay, so now what I'm going to do is, in this expression, that is F dash is equal to Ns minus Nr by 120 by P, I will substitute for what? I will substitute for Ns by Nr. What I will substitute? I will substitute this equation number 2. Okay, so finally what I get is the frequency, that is the frequency of the EMF induced in the rotor F dash is given by, after substitution we will get it as S into F. See, now it is not equal to the supply frequency. When the rotor starts rotating, the EMF induced, that frequency is given by slip times the supply frequency. So this is very important. Okay, and this you call it as slip frequency. So this is the frequency that is happening when the rotor starts rotating. Okay, so slip frequency is given by F dash is equal to slip into supply frequency. This is a very important relation. Okay. Okay, now we will see about what about the EMF. So we found that the frequency is changing. What about the EMF? The EMF will not be the same, right? At standstill condition, it is same like a transformer. So that condition, suppose if the induced EMF is in the rotor, if you are taking it as E2, okay, at the time of starting, that is at time of starting means the rotor didn't start rotating. That time you can take the expression as E2 by E1. This is the expression for the transformer. E2 by E1 is equal to N2 by N1. This will be the expression. But when the rotor starts rotating, what will be the EMF? Will it be E2? It will not be E2. Because you know, in the case of DC machine, EMF is independent of the frequency. But in the AC machines, whether it is a transformer or a three-phase induction motor, this EMF is proportional to frequency. That is very important. That is, EMF is proportional to frequency in the case of AC machines. Okay, so in the case of this induction motor, let's take that initially the EMF, stator EMF, E1 is the EMF induced in the stator, it will be proportional to the supply frequency, right? But what about the EMF induced in the rotor? This E2, that is E2 will be, that is, this is a case when the rotor starts rotating. Okay, so when the rotor starts rotating, the EMF induced in the rotor will be proportional not to F, it will be proportional to F dash, which is equal to proportional to S into F. See, so that term S is coming here. Okay, so that is why we say that when the rotor starts rotating, the EMF induced in the rotor winding is not E2, it is SE2. Okay, this relation is also very important. Okay, now based on this information, we will try to draw the circuit diagram of a three-phase induction motor rotor. First, we will draw the rotor circuit. Then finally, we will draw the, including the stator, we will draw the total equivalent circuit. So here you can see that this is the resistance R2, that is the resistance of the rotor winding. I2 is the current which is flowing through the rotor winding. See here, the EMF is not E2, it is S into E2. Okay, now here you can see another this thing, that is the reactance. It is given by S into X2. So now you may be thinking why this is S into X2. So you know the reactance, right? Reactance and capacitance, they are depending on the frequency. Actually, this X2 is equal to 2 pi F dash into L, right? F dash into L. What is F dash? F dash is equal to S into F, right? So that means this is equal to S into 2 pi F into L. So that is how you get it as S into X2. Okay, so we will see that. Let us consider two conditions. The first condition is standstill condition. When the rotor didn't start rotating, that is at the starting point. You can take the induced EMF as E2 because it didn't start rotation. Resistance is R2. So what about the rotor winding reactance? 2 pi F into L2. Here F is the supply frequency. Why? Because the rotor is still not started rotating. It is a standstill position. Now once you know the value of R2 and X2, you can find Z2. What is impedance? R squared plus X squared, square root of R2 squared plus X2 squared. Now again, how will you find the rotor current? Current is always voltage by impedance. So E2 by Z2. So E2 is there. What is Z2? Z2 is square root of R2 squared plus X2 squared. These are standard equations. That is, then we can find the expression for the power factor. The power factor is given by power factor cos phi is given by R by Z, where R is a resistance and Z is the impedance. This usually we get it from an impedance triangle. You can take it as theta. This will be R, this will be X, and this will be Z. From this diagram, you can get the expression for cos phi and sin phi. Okay, so that is how you get it as cos phi is equal to R by Z. Okay, so cos phi is equal to R by Z, right? So this will be see, sin phi. What is sin phi? Sorry, sin phi. So this will be theta, not this one. This will be theta, right? So sin phi will be equal to what? Opposite side, right? So it will be X by Z. Sin phi is equal to X by Z. So what will be cos phi? I will take this as phi. So cos phi will be adjacent side. Adjacent side is what? This is opposite side, so adjacent side will be R. So it will be R by Z. So this is called the impedance triangle. And from this we can get the value of sin phi and cos phi. Okay. So we take, this is not theta. This is theta. You can take it as theta or you can take it as phi. So this is how you arrive at this expression, that is cos phi 2 is equal to R by Z. Okay, so here it is R by Z. What is expression for Z? Z is equal to square root of R2 squared plus X2 squared. Okay, now let us take the second case when the rotor starts rotating. So when the rotor starts rotating means the frequency is not F, it is F dash. That is given by slip S into F. So now what about the induced EMF in the rotor? It is not E2, it is SE2 because EMF depends on frequency. Which frequency? This frequency. Then rotor winding resistance will be the same. But what about X2? It is depending on which frequency? F dash. So F dash is equal to S into F. So taking S outside, we will get it something like this. See, it is equal to S into X2. Okay. Now Z2, square root of R squared plus not X2 squared. You have to consider the slip. See, when the rotor starts rotating, every time when you write the equations, we have to consider the term slip. Okay. Now, what about the rotor current I2? You have to divide induced EMF by impedance, V by Z. Okay, so here it is S is E2 by square root of R2 squared plus SX2 the whole squared. Now what I am doing here is, I just expanded here. So it is S squared, X2 squared. Next thing is what I am going to do is I am going to divide it by S. So this S will go and here it will come as what? It will be S squared. Right, R2 squared by S2 squared plus S, here one S squared will be there, these two will cancel. So finally what we are getting, E2 by square root of R2 by S the whole squared plus X2 squared. This equation is very important. Now what is power factor? R2 by, because here everywhere it is E2, R2, X2 because we are drawing the circuit diagram of a rotor circuit. Okay, so after that only we will combine both the stator and the rotor circuit and draw the complete equivalent circuit. Okay, now let's see the equivalent circuit, how it is drawn. So here there is R2 and S squared X2, right? Okay. So this is the equivalent circuit. You can see here there is no S term in the induced EMF. There is no S here. S is coming here because we have modified the equation. So this is the R2 by S. You can consider this as the load. Okay, so R2 by S. Now, so you will be thinking how we got this equivalent circuit. It is from here, you can see here. See here the expression which we are getting. What is expression for the current we are getting I2? We are getting I2 is equal to what? I2 is equal to E2 by square root of R2 by S the whole squared plus x2 squared. Actually, this circuit diagram represents this equation. This equation is represented here. See, the current I2 is flowing, and the current I2 is flowing through what all? X2 and what? R2 by S. This is represented here. And what is the EMF here? It is E2. Okay, so this equation is represented by this equivalent circuit. Now we can split this R2 by S into two terms. What is this R2 by S? This R2 by S can be written as R2 by S is equal to R2 plus R2 plus R2 into 1 minus R2 plus R2 into 1 minus S by S. See, if we expand this, what you will get? If we expand this, we will get R2 by S. Okay, so I am splitting this R2 by S into two terms. One is R2, other one is R2 into 1 minus S by S, where R2 is the rotor resistance and this one will represent the electrical load. So we can just modify the circuit. See here, E2 is the induced EMF, X2 is the reactance of the rotor winding, R2 is the resistance of the rotor winding, I2 is the current flowing, and this R2 into 1 minus S by S represents the electrical load. So we have modified it, the equation. Based on after modifying the equation, the same thing is represented in the equivalent circuit diagram. This is the equivalent circuit diagram of the rotor. Okay. Now what we are going to do is we will try to draw the equivalent circuit of the complete three-phase induction motor. Okay, so we will see the complete equivalent circuit. You can see it here. Now this V is the applied voltage. One very important thing is that when we draw the equivalent circuit of a three-phase induction motor, we are actually drawing per phase equivalent circuit diagram. We are drawing the equivalent circuit for just one phase. So this is very important. It is the per phase equivalent circuit. Per phase equivalent circuit. That is very important. Okay. So here V1, I can take it as a voltage which is applied to the stator. I1 is a current flowing through the stator winding. R1 is the resistance of the stator winding. X1 is the reactance of the stator winding. This already we have learned the same thing in the case of transformers also. Okay. Now what about the current I1? It splits into two. One is I0 and the other one is I1 dash, or it is a current which is flowing through the rotor. Here I0 has got two components. Im is a magnetizing component which is flowing through X0. I is the core loss component which is flowing through R0. This is the induced EMF E1 in the stator. Okay. Now we can see about the rotor side. So the rotor side we can see here R2, the resistance R2. R2 is the resistance of the rotor winding. When we transfer it into the stator side, we write it as R2 by K squared, where K is the transformation ratio. Transformation K is given by N2 by N1, where N2 and N1 are number of turns in the rotor and the stator respectively. Okay. Similarly, the reactance X2 of the rotor, when transferred to the stator side, it becomes X2 by K squared. Same thing applies to the load also. So load can be represented as RL dash. Okay. Here this R2 by K squared, we can represent it as R2 dash, which means the rotor resistance referred to the stator. This dash denotes the stator. Similarly, X2 dash denotes the reactance of the rotor referred to the stator, which is equal to X2 by K squared. Now what about the load? Load is given by R to this relation. This relation already we know that RL is equal to R2 into 1 minus S by S. This already we have learnt. And this expression we have to again divide it by K squared. Why? Because we are transferring it to the stator side. That is why this K squared is coming. So this is actually the equivalent circuit of the three-phase induction motor. Now what about the voltage induced EMF in the rotor side? It is E2 by K. Right? Why we are putting it as E2 by K? Because we are transferring it to the stator side. What about the current? It is K into I2. Voltage is E2 by K, whereas current is K into I2. What is the reason? That is, transformation ratio is given by K is equal to E2 by E1, which is equal to I1 by I2. Right? It is inversely proportional, I1 by I2. That is why we are getting it as E2 by K and I2 into K. So this is the equivalent circuit. Now we can just simplify the equivalent circuit. we can bring these things, that is the shunt parameters, to the left hand side. Okay, so when we bring the shunt parameters to the left hand side, it will be something like this. See here. So here you have the no load current I0. Okay, now what will be Im? Im will be V1 divided by X0. That is Im, that is a magnetizing component of the current. Im will be equal to V1 by X0. What about the current IE, that is flowing through the resistance R0? Resistance R0 represents what? The core loss component, that is equal to V1 by R0. Right? Okay. So now here we can see that again we can modify this, right? This is a resistance, this is also resistance. So these two can be put together, right? Similarly, x1 and x2 by k squared, these two also can be combined. So when we combine that, again the equivalent circuit will become further more simple, right? So we will see that. See here. So V1 is applied voltage, we can see here the stator current, then the no load current. See, R1, that is the resistance of the stator resistance plus rotor resistance referred to stator. We write it as R01. So R01 represents what? Equivalent resistance. Equivalent resistance means a stator resistance plus rotor resistance referred to stator side. R1 plus R2 by K squared. Similarly, X01 is the equivalent reactance referred to the stator, which is equal to stator reactance plus rotor reactance referred to the stator side. Okay, so further we have simplified that. This will remain the same. This represents the electrical load. So this is the equivalent circuit of a three-phase induction motor. Okay, so actually why we are using this equivalent circuit is for this help us to analyze the study of three-phase induction motors better. That is why we are using this equivalent circuit diagram. Okay, now later on we will study how to determine this equivalent circuit parameters. That is, there are two types of tests which can be conducted in the case of three-phase induction motor, which we call as no load test and a blocked rotor test. Okay, so what we have discussed today is about the concept of slip. That is, slip is equal to ratio of slip speed to synchronous speed, and it is expressed as percentage given by ns minus nr by ns into 100. Then we learned about the slip frequency, which is given by S into supply frequency. That is, this is a frequency at which EMF is induced in the rotor. Then we learned about the rotor EMF, which is represented as S into ET and not E2. Then the circuit diagram, right? So the circuit diagram we modified. It's in, two conditions are there: standstill condition and rotating. That is, when the rotor starts rotating is the second condition, and we simplified the equations. Okay, we got this as expression, right? I2 is equal to E2 by square root of R2 by S the whole square plus X2 squared. We represent it like this. Later on what we did, we split this R2 by S into 2. That is R2 plus R2 into 1 minus S by S. So this will represent the load and this will represent the resistance of the rotor winding. Okay, and we represent it like that. Then finally we draw the complete equivalent circuit of the three-phase induction motor, including the stator part also. So here you can see the stator as well as rotor resistance, reactance, all the currents, everything we can see. And also we understood that here we are using the term R2 by K squared, X2 by K squared, here also K squared, because we are transferring it to the stator side, where the voltage is like we are getting like E2 by K, current is K into I2. Again we are simplifying it, bringing the shunt parameters to the left hand side. We can find Im and I0. We know the equation, right? Im is equal to V1 by X0. IE is equal to V1 by R0. Then we are bringing all the resistance to one side and all the reactance to one side. Again we simplified. So R01 is equivalent resistance, X01 is equivalent reactance, which is referred to the stator side. Okay, like that we simplified. Okay, now there is one problem which we can do based on this. That is, just we will try to do this also. A 6-pole 50 Hz 3-phase induction motor runs at 950 RPM at full load. Calculate the following parameters. What is the percentage slip? What is the frequency of rotor voltage? Rotor frequency at the slip of 10%. Now the frequency is given F. F is 50 Hz, so you can easily find the synchronous speed 120 F by P. P is also given 6 poles. Now the question is to find the percentage of the slip, right? And also it is given that the motor runs at 950 rpm, which means the rotor speed is given. So you can take it as Nr is equal to 950. So we can easily calculate the slip, right? Ns minus Nr by Ns. Ns already we found it as 1000. Nr is given. We can find the value of the slip. See? Now it is asked next, what is the question? They are asked the frequency of the rotor voltage. What is the frequency of rotor voltage? F dash. That is slip into frequency. Slip we already calculated. What is slip? 5%. So 5 by 100 into supply frequency. 2.5 Hertz. Now the next part of the question is rotor frequency at the slip of 10%. Rotor frequency, same equation, S into F, but here S is changed. Previously it was 5%, now it is 10%, and you will get the frequency. So I hope you got an idea about the concept of slip, then slip frequency, and also the equivalent circuit of the three-phase induction motor.